Inspecting a mega bridge is a maintenance nightmare. We are talking about checking a few bolts. We're talking about hundreds of stay cables, each stretching hundreds of meters into the sky. Current robots are either too small to do real work or too heavy to move fast. But what if the robot wasn't a single machine, but a collaborative squad? In the next 5 minutes, let's take a closer look at CCRobot-S, a collaborative climbing robot squad designed for fast inspection and heavy-duty maintenance of bridge stay cables. The key idea of this system is not a single main robot, it's role specialization. The system is made of 2 parts. The first is the flying platform. It weighs about 30 kilograms and integrates a pose adjustment joint, a flying gripper, and a 7-degree of freedom robotic manipulator. This platform handles all the high-value tasks: grasping, manipulation, and maintenance. The second part is a set of 4 movable anchor bases. Each one weighs about 9 kilograms and is equipped with driving wheels, a gripper, and a customized winch. Their role is simple but powerful. They act as movable anchor points on the stay cable. And this is where the real breakthrough happens. By repositioning these 4 anchor bases, the system can dynamically reconfigure the geometry of the parallel cable-driven system that pulls the flying platform. This directly breaks the traditional assumption that a robot's workspace is limited by its own size. In other words, the workspace no longer belongs to a single robot. It belongs to the entire collaborative robot squad. Building on this hardware architecture, the system is designed around 2 fundamentally different task types, and for each one, it adopts a dedicated motion mode. The first is called the spider-like climbing gate. This gate is designed for heavy-duty maintenance, where high operational stiffness and high payload capacity are required. In this mode, the workflow is as follows. The flying platform is first pulled into the working region by the winches. It then actively adheres to the stay cable, fixing its position. With the platform stabilized, the robotic manipulator performs the maintenance operation. After the task is completed, the platform releases its adhesion, the movable anchor bases redeploy, and the system's workspace is reconfigured accordingly. The second mode is called the zero downtime climbing gate. This gate is designed to push inspection efficiency to its limit. In this mode, the flying platform never needs to stop and perch on a stay cable. Instead, it moves continuously within the region enclosed by the 4 movable anchor bases, while crossing over multiple stay cables for consecutive inspection. As a result, the system can inspect large cable networks without repeated installation and removal, turning what used to be a cable-by-cable process into a continuous, uninterrupted workflow. What really supports both of these gates is not traditional friction-based locomotion, but a controllable adhesion mechanism. The flying platform actively applies a normal force through its flying gripper, generating a shear force that resists slip, instead of relying on the frictional properties of the cable surface. This fundamentally changes where the lifting force comes from. The platform is supported by the combined pulling forces of multiple winches, rather than a single frictional contact point. As a result, the system's payload capacity is decoupled from the condition of the stay cable and can significantly exceed the system's own weight. At the planning level, the authors formulate 2 optimization problems that directly affect system performance. The first is grasp layout optimization. During maintenance tasks, the system selects an optimal grasping position on the stay cable for the flying platform, with the goal of maximizing a metric called the tension factor, or TF. TF measures how balanced and stable the internal force distribution is within the system. The higher the TF, the greater the operational stiffness. The second is anchor reconfiguration optimization. During inspection, the system dynamically adjusts the positions of the movable anchor bases, maximizing the TF of the flying platform along the planned trajectory. This leads to smoother motion and higher quality imaging. Experimental results show a clear trend. The more anchor bases involved in the optimization, the more significant the performance improvement. Finally, let's look at the experimental validation. The research team built a full prototype system and carried out extensive testing. The flying platform demonstrated a 15-kilogram grasping payload and reliable inter-cable crossing capability. Each movable anchor base achieved a traveling speed of over 1 meter per second, supported dynamic loads exceeding 15 kilograms, and has accumulated nearly 500,000 meters of verified travel across more than 500 stay cables on real bridges. Under the zero downtime climbing gate, the flying platform successfully tracked a continuous zigzag trajectory across 3 stay cables, with millimeter-level positioning error, demonstrating its high-efficiency inspection capability. Under the spider-like climbing gate, the flying platform carried a robotic manipulator and tool unit with a total mass of around 30 kilograms, completing heavy load transportation and fixed-point maintenance tasks, which confirms the system's strong, heavy-duty operational capability. To sum up, CCRobot-S brings together an innovative, reconfigurable, collaborative architecture, a controllable adhesion-based actuation strategy, and task-oriented optimization methods. By coordinating these elements within a single system, it successfully achieves high efficiency, heavy payload capacity, and high agility at the same time. This work demonstrates a highly promising solution for the intelligent inspection and maintenance of large-scale infrastructure.
If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.